So we've got a spring, and we're attaching a mass to it. When we attach a mass, it's going to extend the spring. The force that we're applying to the spring is going to be equal to mg. In this case, m is 100 grams or zero point 0.1 kilograms. So we could say the force, the weight, is equal to 0.1 g. Okay, to work out the weight, it's mass times gravity, and mass must be measured in kilograms. So 0.1 g would be the force I'm applying to that spring at that point. And let's just try to let's just see what happens if I were to change the spring constant. If I make the spring constant larger, we get less of an extension. And the reason why we're getting less of an extension is because the spring constant is measuring how hard it is to extend the spring. That's what spring constant means. So if I have a low spring constant, it's much easier for me to stretch the spring. And you can see also they've done a nice little feature where you can see the spring is actually getting visibly less thick. It's getting thinner. So you can see how it's got thicker as I'm extending this, making the spring constant larger. So really thick metal. It's going to be obviously harder to stretch. So that's what having a spring constant, a hard spring constant, means. So with a little bit of playing around, you'll notice that you can calculate the extension of the force necessary to extend the spring. Basically, we're going to have at all times when it's in equilibrium, the force of the spring is going to be equal to the weight, which is equal to mg, which I've just set up here. And with a little bit of experimenting, you'll find that the force of the spring is going to be directly proportional to the extension, which at the beginning, when we first did it, was around about 15 centimeters. And it's actually also equal to the spring constant, which usually has the symbol lowercase k. And so that would mean that the force of the spring is actually directly proportional to kx. There's a little bit of maths that I won't go too much into there, but when that's proportional to that and that's proportional to that, then I can say that that's proportional to both of them multiplied together. And it just so happens that the constant that relates this in terms of proportionality is 1. In other words, the force of the spring is equal to kx. So that's the formula for Hooke's law. Okay, and you can see one of the things they want you to do when this in a related topic is to calculate elastic energy. Now here we have some energy being lost due to heat. But we got gravitational energy and we got elastic energy. But basically, this doesn't really demonstrate it very well. Well, we can see that as I stretch it down, you're going to have a higher amount of elastic energy. And we're saying at this point here, that's where height is equal to 0. It's all relative, really. But you can calculate the elastic energy. And this is just a brief introduction. I'm not going to be proving this yet, but you can calculate the elastic energy. So let's say EE is equal to half multiplied by the spring constant multiplied by the extension squared. So obviously, if you have a thicker spring, which would be a higher spring constant, then you would have stretching it by the same extension would store a greater amount of energy, because you would have had to put a greater amount of energy into the system. Imagine you have like a really thick spring and you compress it or stretch it, then you lock it in place. That spring now has stored elastic energy. It doesn't have any energy stored in it unless it's being extended or compressed. But once it's been extended or compressed, it now has stored energy, and that energy can be calculated with this formula here. Incidentally, I'm stretching it, but I could do the same thing by compressing it. So when I compress it, I also store energy in the spring. And we know that too. We know that if you can get a spring and squash it down, if you release it, it'll turn it into kinetic energy. So that is how to calculate elastic energy, and this is how to calculate the force that would be applied to the spring. Now you can actually derive this equation here, from this equation here, using a graph which I'm not going to go into right now, but I'll probably do, or may have already done it in a previous video. We know that because this is directly proportional, then we're going to have this relationship between x and f. Actually, it should be the other way around, really, because we would have changed the force and measured the extension. And because we know that the work done is going to be equal to force times displacement, or we could say x in this case, you could look at the area underneath the curve, and that would be equal to the amount of work done on it. I won't say anything more, but that might give you enough to be able to work out that equation up here. Incidentally, this graph as well, you can see the gradient of this graph would of course be equal to the change in what's going to be x over f, or the change in x over the change in f. When we relate this one here, we can see that k is going to be equal to f over x. So therefore, our gradient here is going to be equal to 1 over the spring constant if we did that experiment. Let's move that rule out of the way. So, very, very brief video there. I'll just stop it there.